We have 2 more presentations this evening. If you've ever been hiking in the Sky Islands here in southern Arizona and you come across a naturally occurring water source like a spring, it's a really cool thing to see. Aside from that beauty and the sound of that running water, springs are a critical indicator of environmental health and groundwater levels in the aquifer. The ability to track the status of and potentially locate additional springs in the region with a more focused method would be a huge benefit to organizations that study this phenomenon. Presenter Jared Rogers will be discussing such a model with us this evening that could be a big step forward in refining where to locate new naturally occurring springs in southern Arizona. Jared.
Thank you, John. All right, so how this project came about, I started interning with Sky Island Alliance earlier this year, and that eventually turned into this capstone project. Sky Island Alliance is a nonprofit conservation organization that focuses on preserving Major and Sky Islands. And so let me get the formalities out of the way. I'm going to talk about the overview. I'm going to narrow in on my topic, and I'm going to talk about the objectives and concerns. I'm going to talk about how I approached it. I'm going to talk about the data, and I'm going to go to the results, and we're going to go to conclusions and open it up for questions. So when we look at the overall water in the world as a resource, we don't really think about it as much. 97% of all water is saline ocean water. But if we look at that small sliver, that's actually groundwater, which is only 0.61 of all available water. 98% of that is available fresh water to us. And so that has a lot of impact, and we need to pay attention to that. So where do springs come into play? Well, it's like what John said. Springs are an indicator to the groundwater. If we look at the overall hydraulic cycle, groundwater is just as important as the surface. And if we think about it, the aquifer is pretty much just the water table that overflows, and that is what springs are. And if we can find springs, then we can have a better understanding of groundwater flow regime. So, but in order to study springs, we need to find them. And the way it was before, field researchers would go out into the field and just kind of not aimlessly wander, but it wasn't a well use of resources. And if we can come up with a model that could predict spring locations, this would save time and thus make cost effectiveness of resources more efficient, and they can come to results more quickly. So this is the overview of the Major and Sky Islands provided by Sky Island Alliance. So Sky Island is pretty much a unique ecosystem in a mountain region, and the surrounding valley is completely different, hence the Sky Island. And so let me zoom in onto our study area in southeast Arizona. And what's shown is a DEM of my study area. The darker areas are low elevation, and the higher is higher elevation. And these are the springs that are already known in the area. Right now we see 484 springs, and you're thinking like, oh, that's a lot of springs, why are we doing this? Well, this model is to first see if we can do something about that, to see if we can study springs through GIS. So let me get the logistics out of the way. I used ArcMap, the latest version, and SPSS, which is a statistics software program. I projected this into the East Arizona coordinates, so it's the NAD 1983 hard state plane coordinate system in international feet. And all my rasters are set to 30 by 30 cell size. And my approach was using the stepwise logistic regression. That's pretty much a binary approach. So it's either springs are going to be in this location or they're not. And I ended up coming with 14 dependent variables. And I had that springs data, which was shown, and I created random sample points. Then I'm going to do a test on it to see if that is all accurate. And I have to do another follow-up to test to see if the data is even valid, see if the model is even valid. So the independent variable, it's what I've seen, what you guys seen on the DEM. The sample size is 484 total springs. I made another random sample of the same amount, creating a 50-50 ratio. You can choose any ratio you want, but I went up going to 50-50. My dependent variables are, like I said, are 14. So when studying a landscape or an environment, you want more variables to represent that. So the more you have, the closer you have a representation of the realistic environment. And I categorize that into geology, topography, and other. And I left an asterisk on all of them just to signify how I got that data. So it's either I used a raster calculator, I retrieved it from the NRCS website, or I used an ArcMap tool. And the precipitation I got from the Oregon State University PRISM site. But I'm going to focus on the geology dependent variables for the sake of time. And so this is my lithology map. What is shown are 12 different rock types, major rock types, and as well as the faults. So what I want you to get out of this is that faults are known to be openings in the ground, and that's more likely to have water flow through it. And so I want to see if there's an indication between springs and faults. Same thing for geological contacts. A geological contact is when two different rock types are in touch with each other. And so I've come into data where it's either these contacts are either impermeable or just like treat the same as faults. And for the sake of assumptions, I created faults and geological contacts as the same. So what I did is I merged the two polylines, and I created a Euclidean distance tool for that. The second part of this I want you to get out of is that there's 12 different rock types, and that's a lot to take in. And so I wanted to simplify this to see if I can observe any patterns. And so I reclassed them by permeability. Rock types can range from either very permeable or completely impermeable, which is like impassable. And so I did a relative analysis on all these different rock types. But it all varies depending on microfractures and formations. So I had to use some assumptions to decide on this. And so this is the raster that I got from that reclass. And if you notice that impervious and low permeable layers contain most of the springs, and because of this pattern, I decided to make a Euclidean distance tool from those two locations. The next slide is a soil permeability map. This is the soil horizons above the rock types. What is shown is the micrometers per second, or the saturated hydraulic conductivity. And so the darker areas represent faster rates of water flow, and the brighter areas of lower flow. And again, we kind of see a pattern in the soil permeability. So once I have all the rasters assembled, I took the two different springs data, the control and the random sample, or the study springs. I did a sample tool and created a table for each, and then I appended them, getting my table prepped for SPSS. And what I got out of that was this table. And so SPSS had 5 trials of this trial run, and it decided that 5 of the 14 variables were considered significant or below the 0.05 threshold. And the variables that were considered to be significant were the DEM, the precipitation layer, the distance to streams, profile curvature, and the distance to low permeability rocks. And then there's the constant. And so the next part, I had to put that into an equation, which was my springs potential model. I'm going to go back. So I would multiply the raster with their associated respective regression coefficient, and then add those all together, which is all this. And then I would add the constant, or the y-intercept to that. And so when I made the random sample of springs equal to the study springs, that equaled out. So when you take the natural log of 1, it's 0, so I just took the constant. And so I end up getting that raster, which is step 1. In step 2, I did a raster calculator that would rescale this from 0 to 1. Once I got that, I made a conditional statement that would separate values 0.05 and greater and the other to below 0.05. Once I got that raster, I made another conditional statement relabeling those values 0.05 and higher to 1 and everything else below that 0. And once I got that, I did a sample tool to assign all those springs to their associated location that gave them their values. So there would be 0 and 1. So this is what the raster came out. And so the dark areas are considered unfavorable, and the brighter areas are considered favorable. And so from what it looks like, it's about 20% of the original area. So my results for the efficiency test equation, I took that percentage, which was about 21% of the area, which is I did by cell count, and the model ended up finding all but 100 springs in that model. And that came out to be almost 74%, which is considered good. Not great, but not bad. But it doesn't mean anything if we don't test for that, so I had to do a validation test. So I took that original known springs, and I had to separate them into testing springs and control. Again, I did a 50-50 split. And I redid that whole test that I showed you way back when I did that data preparation. I redid all that, but I kept the same original 484 random sample sites. And once I did all that, I added the control points to the tested springs. And I got this equation. So this is for the training sites. I got just over 73%. And for the control sites, I got almost 75%. So what does this mean? All these numbers are very similar, and what that means is that it produced a reliable result, so we can trust this model. It is a good model to fall onto. So in conclusion, the concerns we wanted to do was try to find a way to make our resources more effective instead of just going out into the field and guessing to find springs. We would try to create a model that would help make our resource management more effective. So the approach was using a springs potential model, using logistics regression, and the results came out good. It's a good start. It's the first of its kind for the Madrian Sky Islands, and it's a reliable approach, but it can also be improved upon. And also, what this means is that we can extrapolate this model to the rest of the Madrian Sky Islands, both in Arizona and in Mexico. And for future thought, when field researchers go out and find springs again, they can double check this model and see if these springs do fall into those locations. If not, and we can go from there. Also, like I said, the model can still be improved by doing other methods. You can add other different variables like NDVI, normal difference, vegetation index, and so on. But yeah, this concludes my presentation. At this time, I'll open to questions. Hopefully I stayed under time. No, thank you. Pete. Yes, this one, okay. It did. That was because one of the variables was distance to streams, and so if you zoom in on it, it does look very dendritic, and it does, and that was a big factor in that. But yeah, it doesn't look like 20% of the area, but at least it narrowed it down a little bit. Hey, yeah.
Have you given any of these findings to the Sky Island Alliance, and have they commented on any?
I'm not shown. I've just given the data recently. They haven't looked at it yet. But yeah, it's one of their long-term goals. So yeah, it's definitely going to be applied.
Maybe we can jump on board and explore with them a little bit to see your.
Maybe? No. Yeah. Anyway, any other questions? All right, thank you, everyone.